Welcome to the lecture on real-time systems. So we will look at the real-time scheduling support in the vanilla version of the Linux kernel, and then we'll look at specific real-time algorithms that are implemented by bespoke real-time operating systems. So we will look at the guarantees that they make, because in a real-time system it is the guarantee that matters. That's the main thing. So the first is, we have already discussed the deadline scheduler class, where every task is associated with a deadline. And the priority of this class of jobs is very high. It is just below stop task. So similar to pick next task CFS, right? Next task fair. We have a next task DL that uses the EDF algorithm that we have seen. You maintain a red black tree where every node is basically a job. But of course, if a task is not periodic, it's a one time task, then a job and a task mean the same thing. And so that is where, some leeway has to be given for terminology. Because if we go strictly theoretically in the real time system literature, then a task is basically an entity that spawns jobs. Which means that if you're looking at a periodic task, which is most often considered in a real time system, then it'll create jobs periodically. And a job is a single entity. In the case of Linux, a task is associated with a task struct. So it is basically a thread in that sense. So that is where the meaning has to be inferred from the context. But basically, a red black tree has a deadline scheduler maintains tasks in the sense of a task struct, right? So in this case, one task is one job. So it maintains the shared DL entity structures, right, which are the metadata information for every deadline task, where they are indexed by the deadline. In the sense, the earliest deadline first, the red black tree will quickly indicate in logarithmic time which task it is. It will basically maintain a pointer to this structure via which the task can be identified. And then you can run it. So this basically supports EDF. And the same way, if we had defined a struct list head, and from a struct list head, we could go to the encapsulating data structure. Similarly, for a red black tree, there are macros. So red black tree, similar to list head, we have a RB node. It is a red black node. So we have macros to go to its encapsulating data structure and return it. And basically, the encapsulating data structure would be a shared DL entity from which the task struct can be found. So that is the broad idea. And it's simple. After the deadline class, we had seen the real-time scheduling class, where basically we have a bunch of these real-time priorities from 0 to 99. For every priority level, we maintain a queue. So what happens is that we can look at the highest priority, which is 99, go down to 0. And for every priority level, we look at the queue. So if the queue is non-empty, then first all the tasks in this queue are serviced. Only if all of them block do we look at tasks with lower priorities. So in this case, of course, fairness is not guaranteed, because the notion of priority is taken very seriously, which means that if you have something at priority, let's say 25, first that will run once there is no priority 25 task left which is ready, then only will come down to 24. So this is why, given it's so rigid, it's typically not preferred in a real-time system, but that's how it is in regular Linux. And we maintain a bit vector, one bit for every priority, to indicate whether this queue, associated queue, is full or, is empty or non-empty. So 0 means, let's say, empty, and 1 means non-empty. So we have one bit associated with every priority queue. right? Every so it's not a priority queue, every queue associated with a given priority. So what we do is that while scheduling, we scan this queue. We kind of go down to find the first one. First one would indicate that there is a queue of tasks at this priority level which are awaiting execution. If that is the case, we have two solutions. The first solution is to run all of them in FIFO order, which is the order in which they started, right? Or the order in which they became ready, or the order in which they were queued for the first time. So let's assume that the first time that they were actually queued in a run queue is their timestamp. So we will run them in that order, in, first out order. So we'll scan every queue, every such queue in FIFO order, and always maintain the FIFO order. That is fine. It is just that fairness could be an issue because a task that came in earlier always has a higher priority. And so the normal issue with this mechanism is that the system can become quite unstable. The reason is that priorities are taken way too seriously. Because they are taken so seriously, even kernel tasks that have a reasonably, which either run in process context or in real time context, but with a low real time priority, even they may not get the CPU. So that's why systems become unstable. Nevertheless, let's come back to the other method. The other method is round robin, which means for all the tasks at the same priority, we run each task for a time quantum, then run the next, then run the next, so on and so forth. But we actually do not go to a lower priority. We just among them, we run them in round robin. So round robin, running anything in round robin is easy. So we look at the first entity of the queue, we run it, then we put it at the end of the queue. Then we run the next, put that at the end of the queue, so on and so forth. The other option is that we don't change the queue, but we move a pointer like the WS clock algorithms. But it's just that if new tasks get added, this physical movement kind of is better. And every time a new task is added, we'll of course set the TIF reschedule flag and come back. But the key point with such real-time systems, the previous one and the current one, is that we are not making guarantees. That is because all of these schedulers are running in a generic context. And in the generic context, it is not possible to make guarantees on the type of jobs that are there. It's not possible to constrain them. So a lot of changes per se are not possible. And to the overall system. But if you consider a very constrained real-time system, then the tasks are known, the durations of execution are known, a lot more information is known, which is why guarantees can be made. So let us look at such bespoke real-time systems next. So that's what we'll look at, real-time scheduling with and without a notion of dependencies. So broadly speaking, any real-time system has a classification, right? Of course, every task has a deadline, that's a given. But even within the scope of that, we can have soft real-time systems where, let's say, if a task misses its deadline, the utility or the value that one gets, it reduces, but it does not become zero. So consider an example such as audio or video processing. If you are looking at 60 hertz video, every frame needs to complete within 16 point. So within 16.66 milliseconds, that is when every frame needs to complete, right? That is all the time that we have for actually a frame to complete. So now if let's say a deadline is missed, so what will happen is we'll see a little bit of a jitter and there'll be some amount of visual disturbance. But depending upon how much the deadline is missed and how many frames miss the deadline, the quality will degrade. It may not be substantial. So if I look at, let's say, the task completion time, and that is the x-axis, and let us say the y-axis is the utility. The utility is let's say 1 out of 1 till the deadline. After that, it sort of reduces. If I look at let's an ATM machine where the debit card is inserted, the pin is typed, and then you want the money. If the money doesn't come on time, the transaction gets cancelled, so the utility is zero. But it's not a case of a total failure. So it's a firm real-time system where it's all right that money was not dispersed. So there is no utility. But it's not a case of like absolute system failure. But consider a missile, and a missile misses its target just because a task did not complete on time. That is an absolute system failure, which means that no task can actually miss its deadline. So let us now look at the notion of schedulability, where we will mostly focus on the third kind, which are hard real-time systems that you see in rockets and avionics. So in this case, the tasks are known. So in the real-time literature, as I said, a task can spawn multiple individual jobs. And tasks are often periodic. In fact, most of the beautiful results are in terms of periodic tasks. And their execution time is known and the deadline is known. But the deadline is for each job of the task actually. Say the job was spawned at, let's say, t is equal to 0. Then by when does it have to complete? That is its deadline. In this entire field, the key question that is asked is that if we have a bunch of periodic tasks, where every job that is spawned, its execution time is known and its deadline is known, is the system schedulable? Schedulable would basically mean that no job misses its deadline. What happens is that a lot of theoretical guarantees are made to say that a certain task is schedulable. And these theoretical guarantees are what make the field so interesting because you can say that there is an algorithm A which is schedulable and it is, let's say, optimal in the sense that if a schedule exists, right, a feasible schedule where no job misses its deadline, then this algorithm will find it. So there is also a notion of optimality. But broadly speaking, this is a very theoretical, it's a very theory heavy field. So let's look at what we had seen earlier for the earliest deadline first algorithm, called EDF, namely. So EDF was a uniprocessor algorithm. And we know that EDF minimizes Lmax for a situation where preemption is allowed. And every job has a deadline. And they arrive at different points of time, right? So the arrival times, also called the release times of a job, they are not zero. All the jobs don't arrive at the same time, right? They arrive at different points of time. They are mainly in an aperiodic system. That is where we had seen this. We have seen that it minimizes Lmax. So of course, we can extend this result to a periodic system and treat a periodic system as actually an aperiodic system. That can always be done. And say that we are minimizing Lmax, and if Lmax is less than equal to 0, it means that no job missed its deadline and the system is schedulable. Fair enough, that can be done. And given the optimality, you can always say that if a feasible schedule exists, EDF will find it. That also would be correct, right? I mean, subject to the fact that preemption is allowed and arrival times and deadlines. Well, so of course, every job would have a deadline. And This, of course, can be done, and Lmax guarantee can be made. But it turns out that in periodic systems, we can actually make a more elegant guarantee. That is why when people talk about periodic systems, they tend to ignore the Lmax result because there is a more elegant and more practical result, a more usable result. So here, of course, you are assuming that preemption is allowed, and for computing the schedule as well as for preemption, the overhead is zero. There is no overhead. So let the duration of a job be di, and let its period be capital Pi, which basically means that if the job is released at t is equal to 0, it needs to run for di units, and the next time a job will be released from the same task will be at time Pi for the ith task, right? This is for task Ti. So the typical assumption that is made is that the deadline is the same as the period, which means that by the time the next job is spawned, the current job would have completed. So the deadline is the same as the period. In this case, we can compute the utilization of the system as summation of I is equal to 1 to n, the execution time of the job, which is that what percentage of this time interval does it actually have to execute, divided by pi. So if you think about every job, di by pi is the portion of the time in a period that it needs to remain busy. If I add this quantity over all the tasks, then I will get the system-wide utilization. So this basically means that, let's say if I consider a large enough period of time, then what is the average mean utilization? And this can be computed via this quite easily. So clearly, if the utilization is greater than 1, this means that we need to do much more work than the time that is given to us. So this will clearly never lead to a feasible schedule. And this is a common sense argument, mainly because that there is too little time and there is too much of work. But if the utilization is less than equal to 1, so there is a theorem which is same, an extension of the Lmax result actually, that if a feasible schedule exists, EDF will find it. And also it says that if u is less than equal to 1, a feasible schedule always exists. So this basically means that if the utilization is less than equal to 1, and of course you have preemption, zero overhead preemption, then the set of jobs are schedulable. In the sense, a feasible schedule exists, and EDF, and if you schedule it by EDF, right? So basically, at every point of time, choose that job that has the earliest deadline. If the utilization is less than equal to 1, be rest assured the schedule that EDF will generate is going to be feasible. No job will overshoot its deadline. So, in the certain sense, the entire system will be schedulable, subject to the fact that the utilization is less than equal to 1 and there is zero overhead preemption. In that case, EDF is guaranteed to find a feasible schedule, and EDF can thus be used. So this is the strength of the EDF mechanism. If you think about it, if I were to provide a commentary on this, that all that we need to do for a periodic system is compute the utilization using this formula. If the utilization is greater than 1, then of course some job will miss its deadline. If it is less than equal to 1, we close our eyes and just schedule it using EDF. EDF is guaranteed to find a feasible schedule. The problem with EDF is that priorities are decided dynamically, which means that let us say this job is running and then another job comes with a closer deadline, then immediately you need to preempt this. But it is possible in some other setting, the same set of jobs are executing. And it so happens that this job got delayed and its deadline is another setting where its deadline is very close, right? In that case, actually the former job which belongs to task 1, the other one to task T1, another to T2, T1 would actually have a much higher priority than T2 because T2's deadline is relatively much farther. So the aim here is that the priority is not tied with the task. It's actually tied with the deadline at that point of time. That at that point of time, whichever task's deadline is the earliest, we go with that. But we don't have a system with static priorities where we don't care about the deadline while scheduling. We don't want any deadline to be violated, but the deadline is not a part of the scheduling decision. Instead, the priorities are assigned statically, which is at startup time. So this is much easier a system to manage because we are not dynamically tracking deadlines and assigning priorities and so on, but all our priorities are decided at the very beginning. So we can make the same assumption here, right? That the deadline is equal to the period. And we can say the priority is inversely proportional to the task's period, which means smaller the period, higher the priority. And this is statically determined. It's not a dynamic determination like in the case of EDF. So what happens is that a task now has the same two attributes, the period and the execution duration. For each periodic task, we compute the utilization in exactly the same manner, summation of di by pi. So let us now look at the classic Liu and Leland's result. It says that a set of n jobs is schedulable using this algorithm. This is known as the rate monotonic scheduling. And it's clear why it's rate monotonic because the rate of a task is inversely proportional to the period. And the priority is proportional in this case to the rate, right? So the priority in this case is proportional to the period of the task, right? Priority of task I is proportional to 1 by period of I. And 1 by period can be thought of to be the rate. So it is monotonic in terms of the rate. So for such a static priority system, so it is static priority, but note that there is still preemption. It is just that the priorities don't change dynamically. A set of n jobs is RMS schedulable if, not only if, right? It's a sufficient condition. The utilization is less than n times 2 to the power 1 by n minus 1. So there's a proof for this. You will find it in reference 2. But the key point is that if the utilization is less than this maximum bound, then we are sure that the system is schedulable using RMS, using the priority scheme that we have defined, which means that if n is equal to 2, then the utilization is 0.83. If n is equal to infinity, then this becomes the natural logarithm of 2, which is 0.69, which means that if the utilization is less than 0.69 or 69%, then any combination of tasks is schedulable, right? So because we have enough free space, low utilization means that in a window of time we are executing for some intervals and we have a fair amount of free space. So it's less than 69%, it is schedulable for sure, regardless of the number of tasks. If there are two tasks, this bound becomes 83%. Now the Liu Leyland bound that we saw on the previous slide, that's a very conservative bound. So often we can do better because kindly note that it is a sufficient condition. It is not a necessary condition. The bound is not tight. So let us look at a few more results. So more can be found in this reference over here. So the worst case from a schedulability perspective happens when all the tasks are in phase. means that they start together, right? So all the tasks at t is equal to 0, all the tasks arrive, and then they start together, they are in phase. So that is when the absolute worst case happens. So this can be proven. A proof for this is there in reference number 3. Reference number 3 is not in the book, in the slide set. So we can use the Lehoczky's test that assumes this worst case. And if you can prove that every task meets its first deadline, then you are done. That is all that needs to be done, because in the worst case, if the first job in a task is meeting the deadline, then clearly after that, the tasks do not remain in phase anymore. Not necessarily, unless they are multiples, the phases are multiples of each other. Not, they don't remain in phase anymore. So the scheduling becomes much more rarefied. So there is more space, there is more flexibility for creating a schedule. So that is why what matters is basically the first deadline. So then the set of tasks is said to be schedulable if they are starting in phase and every task is meeting its first deadline. And this can happen even if u exceeds the Liu Leyland bound. As long as these things are happening, we can say that the set of tasks are schedulable subject to this test passing. Now the question is that we can always start all the tasks at t is equal to 0. But how do we verify that for sure every job will meet its first deadline? We need to find a schedule. Clearly, the priorities will be given by RMS, which means that the priority is proportional to 1 divided by the period. And the set of tasks will be schedulable as per the test that I'm just going to outline. So what we do is we arrange all the tasks in descending order of RMS priority. So this basically means that, let's say, task number 1 has the lowest or smallest period. Should actually be smallest, right? That's the right grammar. Then 2, 3, 4, you go till n. So clearly the ith task for all the other I minus tasks above it, they have a smaller period and hence a higher priority. So what I do is that given time t, a time interval t, I find for the jth task, I find all the periods that are fully or partially fitting in it. For instance, if t is equal to 10 and pj is equal to 3, then ceiling of 10 by 3 would actually be equal to 4. This means that 3 full periods are fitting in 10. And so it's essentially 3 into 3 plus 1. So the last one is fitting partially. But let me count that also. So if I consider the worst case, then there will be 4 periods with these numbers within time interval t. Let me assume that the jth task will execute completely for these 4 time intervals. So the total time it is taking, given that we have a single core, is dj, which is the execution time of the jth task, multiplied with this quantity over here, which is the number of periods, both full as well. I mean, n minus 1 of them will be full, and the last one, the nth one, will be partial. So full and, you know, mostly full and one partial, these are the number of periods fitting in time interval t. So this multiplied with dj is the total time that the jth task will execute. Now what I do is if I compute the load on the CPU for the first I tasks, it is the sum of this quantity for the first I tasks. So this can be thought of as the load on the CPU that is placed until time interval t. This is WIT. I can always compute the average load on the CPU, which is QIT, which is WIT divided by T. This is the mean load on the CPU in the time interval T. So let me think of QIT as being the mean load. Now what I can do is that I can try to find a t for every task I. So for task number I can try to find a time period t which is between 0 but not 0 and 0 and its period pi, where the value of qit is minimized, which means that the average load until that point is actually minimized. All right, that is what I want to find between 0 and pi for the ith task. Now, here is a little bit of a leap of faith that I'm doing, but to fully comprehend this, it is important to actually go through reference number 3, which says that the ith task is schedulable if and only if. So, note the if and only if qi, which is the minimum value, qi is the minimum value, right? At this, qi is less than equal to 1. So let us try to understand this intuitively. The exact maths is there in the reference. But let us say that qi is less than equal to 1. That means that at whatever time instant this is, let us say t star, right? So let me maybe like do a little bit of erasing here. So let us assume that at time t star, that is where this gets minimized, qit gets minimized. So I can say that qi t star is less than equal to 1, which would imply, it's an implication both ways, that wi t star is less than equal to. So what is actually wi? Is the total load on the CPU. Right? So the total load on the CPU is the time that will be taken by all I tasks to execute. And this is the maximum load that can be placed on the CPU because even a partial period we are counting. So if wi t star is less than equal to t star, it basically means that the total execution that they need to do is actually less than this time interval. So all of them will finish. So if all of them finishes, that is not very important for us. For us, the most important thing is that the ith task will finish. If the ith task will finish, it basically means that the first job in the ith task is finishing and there'll be no more jobs. The main reason being that the next job will come only after pi, but we are not considering that. So this means that for the ith task, its first job at time t star will finish, which means that it is schedulable. So this is one direction of the proof. The other direction of the proof is assume it is schedulable, then such sort of a T star will exist. That is also not very difficult because just consider the point of time at which the ith task finishes, right, in the reverse direction. And let us say that finishes at time T star. So clearly at that point, the ith task could be done and all of its higher priority tasks would have no more work to do. Again, that is possible if this condition holds. So we can actually prove both ways quite easily. So hopefully this intuition is enough. So now what we can do is that we can consider these values of qi for all n tasks. For all n tasks, if the maximum if the maximum value of qi is less than equal to 1, it means that all the qi are less than equal to 1. So this should be easy to observe. Again, cleaning the ink is due. If let's say max qi is less than equal to 1, it means that for all I, qi is less than equal to 1, which means that all the tasks are schedulable. And this is our necessary and sufficient condition for scheduling. So this is the Lehoczky's test, which actually can prove set of tasks to be schedulable even if they are violating the Liu Leyland bound, because that was conservative, but this is somewhat less conservative. Whatever conservatism comes only because of the expression here, where you are saying that even if it is a part of a period, the task should have fully executed. So this is the Lehoczky's test, and the Lehoczky's test is quite powerful in reasoning about RMS systems. So it is a sufficient condition, no doubt. There are parts of it that are necessary as well. Now, up till now, we were assuming both in EDF as well as in RMS, right, that the deadline is equal to the period. Here, what we will do is we'll look at DMS, which is called deadline monotonic scheduling in reference number 4, where the deadline is not necessarily equal to the period, it can be smaller than the period. So the deadline is less than equal to period. But clearly, the equal to is not of interest to us. We want a case where the deadline is less than the period. What is the best solution in that case? So, what is happening here is that a job will be spawned, and then another job of the same task will be spawned. Before the end of the period, let's say that there will be a deadline here. So, by this point, it needs to complete. Again, by this point, it needs to complete, even though the next job will come here. So we'll tweak our priority scheme slightly. So the static priority in this case is 1 by deadline, not 1 by period, which is 1 over deadline. So it is easy to see how this degenerates into RMS when the period is equal to the deadline. When it is not, it is 1 over deadline. And it is sort of a generalization of RMS. So this does not have a very simple test of schedulability as we had for RMS, which was utilization based. But we still can come up with interesting insights, and the insights are based on the Lehoczky's test. So the first, so you consider for the ith task, right? So let di, capital Di in this case, be the deadline of the ith task. So if this is the deadline, then the ith task should have finished by that point. So the utilization contribution of the ith task could be d small di by capital Di, where small di is the execution time. So this clearly means that if I consider a large deadline, and in a large deadline I consider a smaller duration, which is the time for which the ith task executes, that is the utilization that the ith task is contributing. And let capital I, small I, let this be the interference, which means that the first I minus 1 task, so they are arranged in the same way as the Lehoczky's test. The first I minus 1 tasks which have a higher priority, they would be interfering. Interfering would mean what? It would basically mean that if this is, let's say, when the ith task was released, this is its deadline. It would perhaps execute in some duration here, but then other parts of the duration would be taken up by higher priority tasks, right? Which would basically kind of displace this task and they would execute. So what would happen is that the sum of all of these is equal to the interference. And this interference is time that is being taken away from the ith task because the other tasks have a higher priority. So the interference plus the execution time should be less than the deadline. And this is a common sense condition. It basically means that until the deadline, the ith task finishes execution and the top I minus 1 tasks, whatever they need to do, they do, but we still ensure that the ith task finishes before its deadline. So this formula would hold. Now to compute the interference, we will use this formula, and we have seen this before in the Lehoczky's test, where all that you do is that you compute this quantity, which is saying that for a given time t, how many periods of the jth task either fall completely or partially within it. Even if it falls partially, we assume that the jth task executes to completion, which is why we multiply it with the full execution time. So this is basically the contribution of the jth task. If we add the contribution of the first I minus 1 tasks in time t, this is nothing but the interference. So we have a ready expression for the interference, and we can clearly see where this expression in the Lehoczky's test came from. It basically came from here, which is telling you what is, in that case, it was the CPU load, the first I tasks. You would think about it, the CPU load of the first I minus 1 tasks, right? So let's in fact go there. So this is what it was. WIT is this. So I can say that this quantity is nothing but Wi minus 1t. It is the CPU load of the first I minus 1 task. Just go back, take a look, it's a summation. Come here, take a look, it's a summation, where I is replaced with I minus 1. So this is the total interference. Now we use this simple algorithm to test for schedulability. This will just be introduced. I will not go into the proof of this because the proof is somewhat elaborate, but it uses the same concepts that you assume the worst case is when tasks arrive in phase, and clearly the first deadline matters. But I'll still do a very cursory introduction of this algorithm and then move on to the subsequent slides. And understanding the insight here is quite important. But the mathematical details are also important, which is why the reference number 4 is there. Reference 4 of the slide set. So we need to understand one thing first, that in the Lehoczky's test, we had said that a time will exist between 0 and pi at which qi is minimum. But we had not really given an algorithm to compute qi, right? So we had simply said that one such point will exist. For simple cases, it can be found manually, but an algorithm was not given. So there is more work. So I would point readers to the reference. But in this case, an algorithm is given to actually find those points of interest, those vulnerable points before the deadline. So what we do is we start with a good starting estimate for the ith task. For every task we do this. So let's look at the ith task. For the ith task, the estimate is basically the point at which is the tightest point, which means that we add the execution time j is equal to 1 to I. And so basically, this is the tightest point because the thing is that for I to fully execute, all of its previous tasks should have executed. So this is the earliest at which the ith task can finish execution because they are in phase. So we assume that t, this is the starting value of t. We set the array cont to true and we check if t is greater than the deadline or not. If it is greater than the deadline, then there is no hope. The first deadline has been missed. It is not schedulable. We return false. Otherwise, we check this equation over here, whether the interference for time t plus the deadline is less than equal to t or not. If that is the case, then we are done because clearly before the deadline we have been able to schedule the ith task and we are done. So we set cont to false and then it comes here and it comes out. It goes out, right? So it exits the while loop. If that is not the case, which means that this is greater than it, then there is no point in losing hope because we still have time till the deadline. So let us try with one more estimate of the time. So let us take another point which is tight, which is the interference plus di. So what will happen over here is that this is also another tight point. The reason being that till time t, which was, so we are computing the interference So the interference would basically, even if there's a partial period, it would account for it. And then we are also saying that because the task could not complete by t, we will consider the interfering part. And then, so this t is of course the old t. And then we'll assume the ith task starts after that. So let this be a new point, which is iit plus di, right? So it is important to see, there's an L value, R value issue over here, that this t is basically the old t, right? It's an old estimate of t old. We are computing t new, which is a new value of t based on the interference of t old and the execution time of di. So this is our new estimate. So with our new estimate, if it is not done, we again come back here and compare with the deadline. If we are less than the deadline, then it makes sense to check. So we make a check. If this check is true, we are done. Else we keep on incrementing t. Either this check ultimately becomes true or we exceed the deadline. If we exceed the deadline, we return false because the system is not schedulable. The ith task in particular is not schedulable. Otherwise, we are done for the ith task. We do the same check for every single task. If for any task it is not schedulable, we return false. If it's schedulable for all, we ultimately return true. So the fact is, or the crux of the algorithm here is basically that we are finding these points of interest. So it is the same in Lehoczky's test also. It is not the case that every single point at every single point this quantity qit will get minimized. There are only specific points which are points of interest, and in DMS we do a better job in enumerating them. So this is more like an algorithm and the previous one was theoretical, but the point is very clear that we have a solid test for schedulability, which is not a formula like in the case of RMS, but it is an algorithm. And the key concepts between this and Lehoczky's test is interference, which remains the same. So we are done with the scheduling algorithms for real-time systems. So we will now look at the protocols for resource allocation. So we'll look at the priority inheritance protocol, the HLP protocol, and the PCP protocol. But we will end the current lecture here, and the rest of the protocols will we will look at in the subsequent lecture.